in chapter 3 now, which is linear regression. So what is regression problem? First thing is, right, second chapter what we did was linear classification. We introduced the classification problems. Similarly, we'll be dealing with linear regression. So what is regression? First problem, first definition that should be there. So regression problem is finding a real function for a given training set, right? Similar to classification problem, where training set T is x1 y1 to xl yl, where xi belongs to Rn and y belongs to set y, which is equals to R, right? So the difference between classification problem and regression problem is the set y, right? If set is y is equals to +1 and -1, this is a classification problem. If the set y is equals to complete line R, complete real space, then this is a regression problem. Is this clear? The difference between regression and classification is the set y, the output set. In the classification problem, the output could be only +1 and -1, right? Positive case or negative case. But in the but in regression problem, the set y, the output set is complete real line. So all the problems that we'll be dealing with will now consider y, the output set to be a complete real set. Now, so for that, we'll be formally defining a regression problem. So given a training set T, we finding a real function gx in Rn to derive the values of y for any x by the formula y is equals to gx. This is the regression problem, right? So for a given set training set T में यहाँ पे क्या है, y is equals to set R, right? So the regression problem is to find a real function gx in Rn to derive the values this. So this is similar to classification problems. The only difference is the output set. So geometrically, if we are saying in one-dimensional space, if we are given this output space, we have to find this function y is equals to gx, right? Now, if this gx function is linear function, if this gx function that we are finding, if this is a linear function, then that would be called a linear regression problem, right? So when gx is restricted to be a linear function, then it is called a linear regression problem. So linear regression problem formal definition is, given the training set T, finding a solution. Training set T is that we have introduced above by equation 1. We have to find a linear function gx which is equals to w dot x plus b in Rn to derive the values of y as y is equals to g of x. This is the linear regression problem. So in n-dimensional space, if we are saying a linear regression problem is to find a hyperplane in n plus 1 dimensional space for a given training set T. Any doubt you can ask? Okay. So intuitively what we are doing is, our goal is to find, if we are considering in one dimensional space, so our goal is to find a straight line, right, with a small deviation from these points, right? So therefore the deviation can be very small from these points, but intuitively what we have to find is, we have to find a straight line that would divide it into two regions. Our main aim is that, right? Now small deviation, with small deviation we are considering that there can be a small deviation, right? So therefore there comes the next concept, which is epsilon band hyperplanes and hard epsilon band hyperplanes, right? So for that, the definition of epsilon band hyperplanes is, for a given epsilon bar, we are writing epsilon bar here just in order to differentiate this epsilon from the any epsilon we'll be using in the proof, right? So this epsilon bar is, we have what we have is fixed. For a given epsilon bar greater than 0, the epsilon band of a hyperplane we are given is y is equals to wx plus b, is the set x and y, the point x comma y, where what these satisfy is w dot x plus b minus epsilon star is less than y is less than equals to w dot x plus b plus epsilon star. That means the region between these two these two planes, right? So that means, if we are saying geometrically, if this is the training set, right, if we are given this training set, this is the training points given, right? So if this is the hyperplane we are considering, y is equals to w dot x plus b, then epsilon distance downward from here and epsilon distance upward from here, right? The region, this region would be called the epsilon band, right? This would be called an epsilon band, a distance epsilon from the hyperplane above and distance epsilon downwards from the hyperplane w dot x w y is equals to w dot x plus b. This distance, this region would be called an epsilon band, right? Next definition what we have is of note that region defined above is open. It is not a closed region and therefore it is denoted by dotted lines, right? So this region is open, first thing. Second thing, it does not contains the point x comma y satisfying this equality satisfy करने वाले points इसमें नहीं है, right? Now, since we have defined what is epsilon band hyperplane, next we have is hard epsilon band hyperplane. So the hard, what we mean by hard epsilon band hyperplane is for a given epsilon greater than 0 and a training set t defined by 1, the hyperplane y is equals to w dot x plus b is hard epsilon band hyperplane if all the trailing points are inside its epsilon band. That is, y satisfies this property. Now what we are saying is, in this condition also, if all the training points are inside the epsilon plane, this is the epsilon band, right? And all the training points are inside this training band, this band only, right? These are the training points, these are all inside this hyperplane, right? So therefore this would be a hard epsilon hyperplane, hard epsilon band hyperplane. If by any chance there exists a training point that is outside this epsilon band, right? So therefore this would not be the hard epsilon band hyperplane because one training point is outside, right? So that means all the constraints should satisfy from this band in the epsilon band only, that is minus y epsilon to epsilon, the constraint function should be existing. Is this clear? Hard band and epsilon band, the difference between these and the connection. Now here epsilon is large enough that these, when epsilon is large enough, then there would always exist a hard epsilon band hyperplane, because if epsilon is large enough, then since training set is fixed, assume that this point was outside, then we can, if epsilon is here, then all the points are inside again the epsilon band, right? So therefore when epsilon is large enough, there would always exist a hard epsilon band hyperplane because the training set is finite in number, training set में finite number of points है. So therefore when epsilon is large enough, there would exist a hard epsilon band hyperplane always. Next point we are considering is the value of epsilon bar correspond to hard epsilon band hyperplane should not be too small, because if it is too small, then for hard epsilon band hyperplanes, if the epsilon value is too small, all training points would not be included, right? If epsilon value is too small, it should be large enough that all the training points are included, but it should not be too large that it is overwriting our space, right? So therefore what we have is, it should be large enough, so therefore there should be an optimal value of epsilon, we denote it as epsilon infimum. So our main problem now is to determine this alpha infimum, right, which leads us to this optimization problem, which is we have to minimize this epsilon such that these constraints are satisfied, right? The objective function is minimization of epsilon bar. If epsilon bar is greater than epsilon infimum, if the solution to this is infimum, epsilon infimum, right? If epsilon is greater than epsilon infimum, then hard epsilon band exists, because अगर epsilon infimum, if epsilon infimum was that value जिसके लिए the constraint would be satisfied, right? And this constraint was nothing but the constraint, the definition for hard plane, right? So therefore if epsilon is greater than this infimum value, the optimal value, then hard epsilon band exists, and if this is less than equals to optimal value, then hard band hyperplane does not exist. right? So therefore what we have is, for a given training set T, when there exists a hard epsilon band hyperplane for a small epsilon, we choose that hyperplane as the solution to linear regression problem, right? So whenever there exists a hard epsilon band hyperplane, that would imply key there exists an optimal value, right? So and that satisfies this constraint. So what we do is we choose that hyperplane to be the solution to the linear regression problem. So now main aim, what is left is to find that hard plane, right? Since from this node what we deduce that if we have a hard epsilon band hyperplane, then that would be the solution. So our main aim is now to find the hard epsilon band hyperplane, right? So to proceed with this, we'll convert this construction, because we do not have to solve the linear regression problem because we do not know any method, right? So to solve the linear regression problems, what we'll do is we'll transform these into classification problems, and classification problems we already know how to solve from chapter 2, right? So to solve this linear regression problems, any linear regression problem that we will be finding next, we'll convert the construction of hard epsilon band hyperplane into a classification problem, and we know how to find the solution to classification problem. Then we'll link the solution to classification problem with this hard epsilon band hyperplane, and we'll be done. Any doubt till now, you can ask.